In this video we start to look at how the coefficient of restitution can be used with two-dimensional motion problems involving impacts with a wall. Now remember from Unit 3 that the coefficient of restitution is an experimental law, and that the easiest way of setting up the coefficient of restitution is to regard it as being the ratio of the speed of separation after the collision divided by the speed of approach before the collision. So we'll now consider the impact of an object with a plane. We'll suppose that just before the collision the particle has got a velocity given by the vector u1, u2, which means that the particle is moving with speed u1 towards the wall and speed u2 parallel to the wall. So there's our u1 and our u2, and then we can say certainly the speed of approach of the particle to the wall is u1. Just after the impact, then the particle will be moving away from the wall, so we can suppose that the particle has got a velocity vector of minus v1 in the x direction and v2 in the y direction, which means that we can say that the speed of separation is v1, and in this case then we have got E is the speed of separation divided by the speed of approach, so that is v1 divided by u1. Now if we know that the plane is smooth, then whilst the particle is in contact with the plane, then the reaction of the plane on the particle will be perpendicular to the plane, which means that the impulse acting on the particle whilst it's in collision with the plane will be perpendicular to the plane. So that means that there is no impulse acting parallel to the plane, which means that there will be no change in the momentum, and hence there will be no change in the velocity of the particle parallel to the plane. So let's have a look at an example. We've got a smooth particle of mass 2 kilograms strikes a smooth fixed wall. Its velocity before the particle before the impact is 5 meters per second at an angle of 30 degrees to the normal of the wall. If the coefficient of restitution between the particle and the plane is 0.6, find the velocity of the particle after the impact, the impulse acting on the impact, and the loss of Ke in the impact. So we'll start with a series of diagrams. So we'll have the wall being in the y direction, and we can see there that we've got the velocity before the impact is 5 meters per second, making an angle of 30 degrees to the normal of the wall. During the impact then, since the wall is smooth, the impulse is perpendicular to the wall. After the impact, we have the particle moving away from the wall with a velocity of with a speed of v meters per second at an angle of alpha degrees to the normal. So first of all then, using the x-axis and the y-axis defined in our diagrams, we've got the initial velocity is 5 cos 30 in the x direction and 5 sin 30 in the y direction. And we'll write the final velocity as a vector minus p, q, where p and q are positive numbers. Now, the speed of separation is p, the speed of approach is 5 cos 30, and we know the coefficient of restitution is 0.6. So we can write p divided by 5 cos 30 is equal to 0.6, which tells me that p must be equal to 3 cos 30. We also know that there is no impulse in the y direction, which means that there is no change in the y component of the velocity. So I can certainly say that q is equal to 5 sine 30. So now, as a vector, I have got the final velocity is minus 3 cos 30, 5 sine 30. Which we can evaluate and obtain the final velocity, or the velocity of departure from the wall, is minus 2.598, 2.5. Using Pythagoras, we can find the speed of the particle, which is 3.606 meters per second. That's just the square root of minus 2.598 squared plus 2.5 squared. And then just using trigonometry, we've got the angle there is 43.9 degrees. So we've found the velocity of the particle after the impact. We've got it both as a vector, and we've also got it in this case as a speed and an angle as well. The impulse acting on the particle, well, if we apply impulse equals change in momentum, then the impulse acting on the particle as a vector is minus j0 during the impact, must equal the final momentum minus the initial momentum, which is 2 times minus 2.598, 2.5, which is the final momentum, minus 2 times 5 cos 35 sine 30, which is the initial momentum. And that gives me minus 13.860, which tells me that the impulse acting is 13.86 Newton seconds. And then we've also got the loss in kinetic energy to calculate. Well, that's the initial kinetic energy minus the final kinetic energy, if we're finding a loss in kinetic energy. The initial kinetic energy is a half times 2 times 5 squared, because we know the initial speed is 5. The final kinetic energy is a half times 2 times 3.606 squared. And if we calculate that, we end up with a loss in kinetic energy of 12 joules. Moving on to a second example, we have a particle P of mass 2 kilograms is moving on a smooth horizontal plane with speed 4 meters per second when it receives an impulse of magnitude j Newton seconds in a direction which makes an angle of 180 minus theta with the direction of the motion of P. Immediately after the impulse acts, P moves horizontally with speed 3 meters per second. The direction of motion of P is turned through an angle of 30 degrees by the impulse. We've got to find J and theta. Okay, so let's have the initial direction of motion of the particle being in the x direction. Now, we're told that the particle receives an impulse of magnitude j Newton seconds in a direction which makes an angle of 180 minus theta degrees with the direction of P. And immediately after the impulse acts, P is moving still horizontally but with speed 3 meters per second and has been turned through 30 degrees by the impulse. And we've got to find the values of j and theta. So we can find the initial momentum and the final momentum of the particle, and we can now use the fact that impulse must equal change in momentum. So initial velocity 4,0. The impulse as a vector is minus j cos theta, j sine theta. The final velocity is 3 cos 30, 3 sine 30. Impulse equals change in momentum now gives me j must equal 2 times the final velocity, which is 3 cos 30, 3 sine 30, minus 2 times the initial velocity 4,0. In other words, we've got j must be minus 2.8043. So we've found the impulse as a vector. A quick diagram of the vector j will help us find the magnitude and direction of the vector j quickly. So Pythagoras gives me that the size of the vector j is going to be 4.11 Newton seconds, and the value of theta, well, we're going to have tan theta is 3 divided by 2.804, so theta is 46.9 degrees. Soon after receiving the impulse, the particle P hits a smooth wall, which is parallel to the original direction of motion of P. After this impact, the speed of P is 2.75 meters per second. Find the coefficient of restitution between P and the wall. Well, again, we need to extend our diagrams now. So after the impulse, we had the particle was moving with 3 meters per second at 30 degrees to its original direction. It then hits the wall, and in hitting the wall it receives an impulse perpendicular to the wall or normal to the wall because the wall is smooth. And then afterwards we'll have it moving with speed 2.75 meters per second in an unknown angle, which at the moment we're going to call alpha. So our velocity v there we already know is 3 cos 30, 3 sine 30. The final velocity we can write as 2.75 cos alpha minus 2.75 sine alpha, and since there is no impulse in the x direction, there is definitely no change in the x component of the velocity, which tells me straight away that 3 cos 30 must be the same thing as 2.75 cos alpha. In other words, cos alpha is 0.9448, so alpha is 19.13 degrees. Now E is the speed of separation divided by the speed of approach. The speed of approach is 3 sine 30. The speed of separation is 2.75 sine alpha. So E is 2.75 sine alpha divided by 3 sine 30, which gives me 0.601. Example 3, we've got a smooth sphere of mass 0.25 kilograms is moving with speed 8 meters per second on a smooth horizontal ground as it approaches a smooth vertical wall at an angle of 60 degrees and is deflected by 90 degrees by the impact with the wall. Calculate the coefficient of restitution between the sphere and the wall and the speed of the sphere as it leaves the wall. Well, again, we need some diagrams. So, setting up the y-axis to be the direction of the wall, we've got our particle approaching the wall at an angle of 60 degrees to the wall. After the impact, the particle has been deflected through 90 degrees and is moving with speed little v meters per second. So we can now start writing some vectors down. We've got the initial velocity is going to be 8 cos 30 in the x direction and 8 sin 30 in the y direction. The velocity after the impact can be written as minus little v sin 30 in the x direction and little v cos 30 in the y direction. So, the fact that we know there is no impulse in the y direction tells me that there is no change in the speed in the y direction. So I've got v cos 30 must be the same as 8 sin 30. In other words, v must be equal to 4 divided by cos 30, or 4.6188 meters per second. Now I found the speed as it leaves the wall. I also want the coefficient of restitution between the sphere and the wall. So E is the speed of separation divided by the speed of approach. The speed of separation is v sin 30. The speed of approach was 8 cos 30. So I've got E is v sin 30 divided by 8 cos 30, which gives me 0.333. And that concludes our first look at coefficient of restitution, and we'll have another look at coefficient of restitution in the next video.